Hi, I'm Rainer Banowitz, and it's my pleasure to be here to talk to you about our work on developing a rule-based machine learning approach to survival analysis. This work was originally a chapter of the PhD thesis of first author Alexa Woodward under the guidance of Dr. Moore and myself. It's based on some of my previous work in developing learning classifier systems focused on supervised learning. Let's start with a summary of this project as a whole. Our big picture goal is to be able to interpretably model complex associations, such as epistasis and heterogeneity, in biomedical survival analysis. The goal of this study in particular is to provide proof of principle work in trying to adapt a learning classifier system, which is an evolutionary machine learning modeling algorithm, to survival analysis. LCS, or learning classifier system, learns a model as being a set of discovered if-then rules. This study includes simulating genetic survival datasets, implementing and applying our survival learning classifier system, and exploring visualization strategies to interpret underlying complex patterns of association. To summarize our results, we found promising performance and interpretability on simulated genomic survival dataset scenarios. The overall contribution of this work is to introduce the first rule-based survival model, capable of modeling complex associations and providing multiple avenues for model interpretation, including patient survival curve prediction. This algorithm was also set up to have flexible data handling, including working with mixed feature types, data missingness, and scaling up to larger datasets. Biomedical data comes in many forms, such as genomic data or other omics, electronic health record data, time series data, image, and natural text. All of these data sources can represent features of interest. A common goal in biomedical data science is to connect this pool of features with target clinical or medical outcomes of interest. These relationships between features and outcome can be simple, such as univariate or Mendelian relationships, or more complex, including pleiotropy, epistasis, and heterogeneous patterns of association, or some much more complex combination of any of these. Ultimately, the goal is to make predictions on outcome and understand the underlying patterns of association connecting features to outcome. One modeling strategy that we've explored in previous work includes learning classifier systems, or LCSs. These systems use if-then rules to create what I call piecewise models. To illustrate how learning classifier systems model a problem space, consider this simple classification example, where we're trying to classify the blue circles from the red X's. Learning classifier systems discover rules that cover parts of the problem space, ideally as accurately as possible, with the if part of the rule determining the region of the problem space that the rule applies to, and the then part of the rule determining what class prediction will be made. We've shown in previous work that these systems can model and interpretably characterize complex biomedical associations in classification problems. As a bit of background for this study, let's talk about right-censored survival analysis. Here we have illustrated a Kaplan-Meier survival curve, where we have two groups of subjects, labeled here as low risk and high risk. On the y-axis, we have survival probability, which is the proportion of instances within a group that have survived up to the time point illustrated on the x-axis. We can make comparisons between these two survival curves to determine whether there are differences in survivorship between them. This plot assumes that we know the time of the event, let's say death, for every instance in our dataset. However, in real-world data, we often have an extra layer of complexity, which we refer to as right censoring. Let's assume we set up a study to collect data on instances to try and compare survival risk. This study will typically have a definitive time at which the study ends. In other words, observations stop being made. So for some instances in the data, such as IDC and IDA, the event in question happens before the end of the study and we observe it. However, for some instances, like IDB, the event in question might have occurred after we stopped making observations about our study group. So we only know that the individual had the event past the time of the end of our study. In other words, we know that IDB survived at least this long, which is still some useful information. Other times, subjects drop out of a study early. And again, we know that they survived up until a point, but there's ambiguity after. So for all of these instances, we collected a time. But this time can represent a time till the event was observed, or the time until the event of censoring. So now we're going to add some censored instances to this initial example. Censored instances show up in this survival curve as vertical lines on the survival curves themselves. When added to this plot, they increase the uncertainty in the confidence interval around these survival curves. since there is added uncertainty as to when the actual event of interest took place. Here's what an instance would look like in an example survival dataset. Here we have the feature values of columns in the dataset representing features. We have a time, which is our primary outcome, for example, time of death, and we have a column for our censoring information, given as 0 or 1, where 1 means that the event was actually observed, and 0 means that censoring took place at that time. With respect to previous work in survival analysis, the Cox Proportional Hazards Regression Model, or CPH, is a widely used approach, which has allowed broader application to data with many independent variables. But the CPH and its derivative methods rely on multiple assumptions, including the assumption of proportional hazards, linearity, and additivity of predictor variables. Some machine learning algorithms have also been adapted for survival analysis, including support vector machines, random survival forests, and deep learning. On whole, these methods have suggested improved predictive accuracy, but have other limitations. For example, all of these methods lack interpretability. Also, the random survival forest splits data using the log-rank score, which also relies on the proportional hazards assumption, and deep learning requires large sample sizes to train, which are often not available in biomedical datasets. And to date, none of these have been optimized to detect and characterize heterogeneous and epistatic associations in data. So now let's talk about our survival learning classifier system. This system is based on our previous extracts algorithm, which is a supervised learning descendant of the well-known XCS learning classifier system. And more specifically, as a supervised learning approach, it has a lot of similarities with the UCS learning classifier system. Overall, much of the architecture is the same as traditional learning classifier systems, with rule discovery being driven by a genetic algorithm and covering mechanisms. Michigan-style learning classifier systems in particular take an instance-wise approach to learning, focusing on one instance from the dataset at a time. The model itself is captured by a population of if-then rules. Rules are initialized with a covering mechanism, and evolutionary learning cycles follow the flow of forming a match set, separating that match set into correct and incorrect sets, updating rule performance and fitness, applying subsumption as a generalization pressure, and discovering new rules with the genetic algorithm, selecting parents, and applying crossover and mutation to discover newer and better rules. If you want to learn more about what makes learning classifier systems different from other standard genetic algorithms, check out this video we put together called Learning Classifier Systems in a Nutshell. Our Survival-LCS also draws inspiration from our previous work on extending LCS algorithms to continuous endpoint prediction, and work in developing a multi-objective rule fitness function that is Pareto front inspired, using a combination of an adjusted accuracy and an adjusted correct coverage as the two primary objectives underlying the fitness function. Another difference between Survival-LCS and other learning classifier systems is that while a learning iteration still focuses on one instance at a time, any new rules introduced by covering or the genetic algorithm are immediately batch evaluated on the entire training dataset. This is something we can confidently add, given that this system is focused on supervised learning rather than reinforcement learning. Now let's focus in on some of the key differences between our algorithm and other LCSs. First, with respect to rule representation and forming a match set. Here we have the example instance from a survival dataset. Survival-LCS represents a rules condition much like other standard learning classifier systems. But as an action, rules learn to develop some event interval, or in this case a time range, with a minimum and maximum value. With Survival-LCS, we're not just trying to predict a specific outcome value, but potentially capture outcome value ranges that are informative. This can often be valuable in biomedical problems, where it's enough to predict if some outcome will be in a high range versus low range, rather than having to predict a specific outcome value. Here we show some other example instances in our survival dataset. Matching focuses on the features that are specified in a rule. We check to see if this specified instance value in the rule matches the corresponding instance values in any of the instances. In this case, the last instance value doesn't match. But for the three other specified rule positions, we have all matches. Therefore, in this example, the top three instances match this rule, and the last one doesn't. Note that in determining matching, we ignore the event interval and the time and censoring information. Now let's look at forming a correct and incorrect set from the match set. From here on, we'll represent correct or incorrect event intervals as such, with either the white interval or the striped interval. Let's first look at two instances where the event was observed. To see if our given matching rule falls into either a correct or incorrect set, we're going to focus on its event interval. In the first instance, the event time falls within the event interval range, and therefore this rule would be put in the correct set. In the second, the time falls outside of the event interval range, and so it would be put into the incorrect set. Now let's look at a couple more complicated cases where the endpoint was not observed or we had censoring. So in this first case, the instance's time falls before the event interval. And in this case, Survival-LCS would put that rule into the correct set. While there is ambiguity here as to when the actual event occurred, this rule is as correct as we can hope for, given that at least it predicted that the event would happen sometime after this instance's time point. Had this time been after the event interval, this rule would have been put into an incorrect set. And lastly, if the time point of a censored instance falls within the event interval range, we also assign it to the incorrect set. Now this is a bit of an assumption being made by Survival-LCS, but we're basically speculating that the actual event time was unlikely to have fallen within this event interval, but more likely afterwards. Now let's step back and look at correct and incorrect sets across a number of rules. First, we'll look at training instances that were not censored, and we know the event happened at this given time point. These shapes show different event intervals for matching rules in our rule population. We can see that rules with an event interval that captures the event time would be placed into a correct set, and rules with an event interval that doesn't capture the event time point would be put into an incorrect set. Differently, in dealing with a censored instance, we know that the event happens sometime after this time point, but we don't know exactly when. This is why we're only assigning rules with an event interval after the censored time into the correct set, and those that overlap with the censored time, or fall before it, into the incorrect set. This helps us mitigate some of the censoring uncertainty that's present here. But again, this is proof of principle work, and there could be more clever ways to deal with these scenarios. Another important aspect of Survival-LCS that differs from other learning classifier systems is how the rule parameter updates take place. As mentioned, Survival-LCS uses batch updates of rule parameters across the entire training dataset the moment they're introduced into the population. To update the parameters of a given rule, we first find all the instances that it matches, and separate these instances into having put the rule into either a correct or incorrect set. However, since we're trying to predict a quantitative outcome, in this case time, we can't just use a standard rule accuracy calculation of the correct set count divided by the match set count. Otherwise, we'd end up with rules with an event interval that span the entire outcome range. So to deal with this, we incorporated a prediction error into the rule's accuracy calculation. Specifically, a rule's accuracy is the sum of 1 minus the time prediction error across all matching instances divided by the number of matched instances. This error term is scaled to have a value between 0 and 1, and we'll take a look at it more closely on the next slide. And to calculate rule fitness, we use some of our previous work exploring Pareto-inspired rule fitness, balancing two separate fitness objectives: useful accuracy, which is the rule accuracy beyond what we'd expect by random chance in the dataset, and useful coverage, the correct instance coverage, also beyond what we'd expect by random chance in our dataset. These dots on the plot represent individual rules discovered by Survival-LCS, and their fitness is proportional to their distance to the closest point on the Pareto front. Pareto-inspired rule fitness is an example of an adaptive fitness function, since the fitness landscape changes as better and better rules are discovered, forming a new front and triggering a recalculation of the rule fitness of all rules in the population. Now let's take a quick closer look at how we calculated error in instances that were not censored and were censored. If the rule was in the incorrect set, error was set to a maximum of 1 by default. If it was in a correct set, error was calculated with the following equation, where given an event interval with a maximum time and a minimum time, we focus on the event interval center, which serves as a default specific time prediction for the rule, and we calculate the relative distance between the event interval center and the instance's observed event time. And this is scaled by a maximum distance of the event interval center minus the minimum time. This way our errors always fall between 0 and 1. Turning to censored events, we have two scenarios to deal with if the rule fell within an incorrect set. If the interval was before the censored time, then the error again is set to a maximum scaled error of 1 by default. But if the interval overlaps with the censored time, then the error is calculated as 1 times the proportion of the rule interval known to be inaccurate. In other words, the proportion indicated here by the red arrow. And lastly, if the censored event was in a correct set, the error was set to 0 by default. Again, this can introduce some error on the part of the algorithm, but since we don't know when the actual event took place, we have no basis to determine how much error there was for this rule. Now let's talk about how Survival-LCS makes predictions after it's been trained. Ideally in this study, we wanted to be able to predict event times for a given instance, as well as to output instance-level survival probabilities over time. Or in other words, come up with a survival curve prediction for every new test instance. First, let's look at predicting the event time. In this illustration, we show the event intervals of rules that matched a given testing instance. And we use the boundaries of these intervals to define new candidate intervals. For every one of these candidate intervals, we sum up rule votes based on the underlying numerosity and fitness of each rule that matched. And this helps us define a candidate interval with the strongest support. Once we have the best interval, we select the center of this interval to serve as the default prediction for a given testing instance. The strategy we came up with to predict survival probability over time is a little more complicated. For this, we're going to rely on using kernel density estimation. We look at the event times for training instances that were also matched by these rules that match the current testing instance. And we can see these training event times plotted here. From this, we plot a density of matching event times, which then can be turned into a probability density function, or PDF. Lastly, we take the integral of the PDF to get the cumulative density function, or CDF. And 1 minus the CDF gives us the predicted survival curve for an instance, which in this case looks like this. And so here we have a predicted survival curve for a given testing instance. To evaluate our Survival-LCS algorithm, we decided to focus on Brier scores, which measure the accuracy of probabilistic predictions. Brier scores capture both discrimination and calibration, unlike C-statistics, which only captures discrimination. It averages the squared distance between the observed survival status and the predicted survival probability, giving a value between 0 and 1, with 0 being the best. And to account for censoring, the squared distances are weighted using the inverse probability of censoring weights. Of note, a potentially useful model must have a Brier score and upper confidence interval below 0.25. Ultimately, in this study, we used an integrated Brier score, which is the average of score values for the interval, as our primary metric for evaluating Survival-LCS. In this study, we focused primarily on simulated survival dataset experiments. We simulated genomic datasets with different underlying patterns of association, including univariate, heterogeneous, epistasis, and additive effects. We also simulated datasets with different numbers of features, including 100, 1000, and 10,000, and different frequencies of censoring in the data, including 0.1, 0.4, and 0.8. And lastly, we looked at the effect of different minor allele frequencies of either 0.2 or 0.4. All of these datasets had 1,000 instances in each, and were simulated with pretty noisy signals. Also in all the experiments, we used 5-fold cross-validation. For the datasets with only 100 features, we further applied permutation testing using 100 replicate runs, and for comparison, trained Cox proportional hazard models to compare to our Survival-LCS approach. We limited these analyses to the smaller datasets due to computational restraints, and the fact that the CPH approach couldn't run at all on the larger datasets, highlighting an immediate limitation for that existing, largely utilized methodology. Key parameters for our Survival-LCS algorithm, including using 50,000 training iterations, and a population size of 1,000. And lastly, we employed LCS Dive to explore characterizing and visualizing the associations in the different datasets that were discovered. For the purposes of this talk, I'm just going to focus on the results on datasets with only 100 features. In each of these tables, our primary evaluation metric of interest is IBS, as well as its corresponding lower and upper confidence interval bounds. Each table represents one of the 4 different underlying data configurations: univariate, epistatic, additive, and heterogeneous plus epistasis datasets. In these tables, bold results highlight where Survival-LCS significantly outperformed Cox proportional hazard models based on the mean IBS, and shaded values indicate where permutation testing yielded significant performance. To summarize the results, first and foremost, we found that all confidence intervals for IBS overlap between Survival-LCS and the Cox proportional hazard model, suggesting that while Survival-LCS wasn't doing a better job predicting survivorship, its performance was on par at least with Cox proportional hazard model. In applying Wilcoxon rank sum test comparisons between different groups of results, we found significant difference between Survival-LCS models on these different patterns of association, with the additive models performing best, which is what we would have expected, and heterogeneous datasets performing the worst, which again was expected. We also observed a significant difference between using different censoring proportions in the simulated data, with lower censoring performing better, again, as would be expected. We observed no significant differences across the number of features or minor allele frequencies in these analyses. Now let's take a look at the prediction of survival probability distributions in action, using one of the epistatic datasets. The survival curve on the right shows the individual instance survival predictions on the 1,000 different instances. Focusing in on a couple feature interactions in this model, when both features had a value of 1, the instance would have a higher survival time in the data, and when feature 1's value was 1, but feature value 2 was 2, it would have had a particularly low survival time. So this figure starts to illustrate how the individual survival curve predictions capture different parts of this underlying epistatic model. Turning to model interpretation, let's look at some of the rules that were evolved by Survival-LCS on one of the epistatic datasets. Here we've ranked the rule population by numerosity and are displaying the top 10 rules. Features that were simulated to be predictive in the dataset start with an M, and those that were noisy features start with an N. We can see that some of the highest accuracy rules that were discovered correctly capture this two-way epistatic interaction between the two predictive features in this dataset. Another visualization we explored in the context of Survival-LCS was generated using LCS Dive, which creates a network rule population visualization. This is done in an attempt to capture underlying complex patterns of association, such as epistasis and heterogeneity. In this example, we're looking at an epistatic dataset. In this network visualization, the node's size represents the frequency that a given feature has been specified in rules of the population, and the edge size represents the frequency that a pair of features were co-specified in rules of the population. And in looking at the rules discovered by Survival-LCS on the epistatic dataset, we see that the algorithm has successfully focused on these two predictive features the most over all other noisy features, and that they tend to be co-specified together in rules, better capturing the underlying interaction effect between them. One final visualization we explored using LCS Dive is to examine feature tracking scores. We previously introduced this idea of tracking feature importance at the instance level during the course of LCS training. Then, after algorithm training, we can take these scores and apply hierarchical clustering in order to identify important features, characterize interactions, and characterize heterogeneous instance subgroups. We again looked at having run Survival-LCS on an epistatic dataset and found that across different instances, it placed particular import on those two interacting features above all other features in the dataset. Lastly, let's talk about some of the limitations we observed in applying Survival-LCS to these simulations. First off, we did find some poor results, where the IBS, or the upper confidence interval, was above 0.25. Closer inspection revealed that these simulated datasets tended to have highly skewed true event times. Currently, Survival-LCS only has a limited amount of algorithm pressure to narrow rules' respective prediction intervals. Therefore, Survival-LCS can be sensitive to the underlying data distribution. This can make it biased towards event times that are more spread out, since sufficiently narrow rules could be excessively penalized in more skewed data scenarios. Furthermore, in this study, we only trained Survival-LCS on up to 50,000 training iterations. And given the complexity of some of these datasets, and the requirement to find both the right condition and event interval ranges, we fully expect that we can achieve better performance with a larger number of training iterations. So in conclusion, this work provided a proof of principle demonstration of how learning classifier systems can be extended to model complex associations in survival data with censoring, to interpret or characterize those associations, and predict not only survival times, but survival probability distributions for new instances or testing instances. All of our prototype Survival-LCS code and the survival data simulation code is available on our lab's GitHub page at the following link. And through this work, we've identified a number of opportunities for improvement for our future work, including improving the underlying data simulation strategy that we employed in this study, and expanding the simulation study to a wider variety of scenarios, to examine alternative accuracy and fitness metrics to help promote ideal predicted intervals for target problems, and the need to consider combining Survival-LCS with effective rule compaction or rule subset discovery methods. With that, I'd like to thank all of the co-authors on this paper, including first author Alexa Woodward, who led this research project as part of her PhD thesis, Harsh Bandhay, a data scientist in my lab, who updated the code, replicated all of the analysis, and helped prepare this manuscript for publication, and Dr. Moore, who also provided mentorship and ideas furthering this project. I'd also like to acknowledge 2 NIH grants that helped fund this work, and point you to our lab's YouTube channel with educational videos on artificial intelligence and machine learning, and our lab's GitHub page with all of our open source software. Thank you so much for your attention. Please feel free to reach out to me if you have any further questions, or you're interested in collaborating in the future.